So let's start the final review. We'll start with heat exchangers. So for heat exchangers, there are three main equations. One of them is the log mean temperature difference equation. This one comes from Q equals HA, Ts minus T infinity. Basically, this is the correct version of that equation. You can't use Ts and T infinity with the heat exchanger because there's internal flow and there's no such thing as a free stream temperature. Also, because of the heat exchange along the length of the tubes, right, it's changing the temperatures, so you need to use the log mean temperature difference. U is the overall heat transfer coefficient. Okay, here's the definition of the log mean temperature difference. Again, you can switch location 1 and location 2, but you have to be consistent. So if you put location 2, then 1, then for the natural log, it should be 2 first, then 1. Likewise, the way I taught it in lecture, you put location 1 first, then 2. In the ln, location 1, 2. As long as you stay consistent, you'll always be correct. Parallel flow heat exchanger is the most straightforward one. In this case, location 1 is the inlet for both fluids. Location 2 is the outlet for both fluids. So we can just, for delta T1 is TH1 minus TC1. That turns out to be just THI minus TCI. Pretty straightforward. Same thing for delta T2. It's just TH2 minus TC2, which is basically THO minus TCO. Done. Very easy. Things get a little bit more interesting with the counterflow heat exchanger, because here location 1, location 2, right, the inlet for one fluid is going to be the outlet for the other one. So how do you know which one to pick? It turns out it doesn't really matter which one you pick, but just for the sake of consistency and keeping things careful, I highly recommend that location 1 you use for the hot fluid. Okay, you should put location 1 for the hot fluid. That's the tradition. So that means that location 2 would correspond to the outlet of the hot fluid. So basically delta T1, I like to write it first TH1 minus TC1. So location 1 for hot fluid, that's your inlet, but that's going to correspond TC1 to the outlet of the cold fluid, like so. Likewise, you can do a similar thing for delta T2. It's TH2 minus TC2, but TH2 is THO. TC2 would then correspondingly be TCI. Okay, as long as you're consistent, you should be good. For the same inlet and outlet temperatures, your counterflow heat exchanger will have a large, it'll be better basically. And the reason why is, one of the reasons why is because your log mean temperature difference for the counterflow is greater than for parallel flow. Okay. Overall, your counterflow heat exchanger will exchange more heat, which means if you want to exchange the same amount of heat as a parallel flow, you can actually make a counterflow smaller and it'll transport the same amount of heat as a bigger parallel flow because it's more efficient. Mass flow rate is related to the overall heat transfer coefficient in the sense that if you increase the mass flow rate, you will increase the overall heat transfer coefficient. So the equation, with the log mean temperature difference, in other words, this one, UA, this one, that's one of the heat exchanger equations. The other two useful ones are the mass flow rate equations, which look something like this. Okay, one is for the cold fluid, one is for the hot fluid. All of them are equal to Q, and all those Q's are equal. The cold fluid, right, the energy that the cold fluid gains comes from the hot fluid. So that means that this Q, by conservation of energy, must equal this Q. Likewise, the UA delta T log mean equals Q. That Q also is equal to these. So once you have all those three equations, you can pretty much solve anything. The only thing you need to be careful of is if the cold fluid or the hot fluid is undergoing a phase change. If it's undergoing a phase change, the inlet and outlet temperatures are going to stay the same, right? So you're going to end up with 0. So what's the problem? Basically, then you would need to change your equation to have, instead of m dot Cp, you have m dot times the enthalpy of vaporization or enthalpy of boiling. Let's look at this heat exchanger equation. I basically solved this heat exchanger. So this is a parallel flow heat exchanger and I calculated delta T log mean, and I would do the same thing with a counterflow just to prove to you that the counterflow has a better log mean temperature difference. So let's go ahead, right? So first you would do your, TH1 minus TC1, THI minus TCI. For the parallel flow, it's really easy because location 1 is inlet for both fluids. Likewise, location 2 is outlet for both fluids. Here you go. That's your delta T1. You can do a similar thing with delta T2. Then you can plug that into your log mean temperature equation, log mean temperature difference equation, and you get your log mean temperature difference. For the counterflow, it's a similar process, but you just got to be careful. Delta T1 is TH1 minus TC1. What's location 1? I have it here. I labeled it here, but on the exam, you're not going to have the label. So remember, location 1 corresponds to the inlet of the hot fluid. Okay, location 2 would be the outlet of the hot fluid by tradition. All right. So basically, TH1 is basically THI, which would make TC1 TCO. Here are your values. Similar thing for delta T2, TH2 minus TC2. We have basically THO minus TCI, and there you go. So now we can plug it into the log mean temperature difference equation, and we get our answer. You can double check these numbers yourself. You'll see that the counterflow log mean temperature difference is much larger, or I should just say larger, than the parallel flow. For this question, I got bored, so I wanted to ask a follow-up question. Follow-up question was how much heat is absorbed by the water for the counterflow heat exchanger. So you have one of three options to find Q, right? You either have Q equals UA delta T log mean for a counterflow, or you could use your m dot Cp for the cold fluid, or m dot Cp for the hot fluid, right? One of these three equations. Any of them would work. Now, the idea is that in this particular question, only one of those equations will work because you only have information for that one. So basically, the only equation that that'll work is the m dot equation for the cold fluid. So you can go ahead and do that, plug in your values, and you get your Q. What if we have something weird like this, which is actually not really weird. This is a more common type of heat exchanger. It's basically a cross-flow heat exchanger. So anytime you have a cross-flow or shell and tube or multi-path, any like difficult heat exchanger, we solve it using correction factor. Basically, what we do is we assume that the log mean temperature difference is counterflow for all of these, but then we have to correct it with a correction factor. And we can find the correction factors in this chart, basically. There's a whole chart in the notes that I gave you. You can take a look at, and you'll see which charts apply to which cases. So in here, the hot fluid we're assuming is boiling. So the inlet and the outlet for the hot fluid is constant because during a phase change, your temperature stays constant. In this case, whenever you have boiling or condensation, there's a phase change happening, your correction factor turns out to be 1. So you're lucky in that case. You don't have to do any complex, any type of calculation. And here you would just go ahead and do the normal log mean temperature difference again, treating it as if it were counterflow. So delta T1 is TH1 minus TC1. TH1 for counterflow, right, is THI, which in this case is 100. Okay, TC1 is TC outlet, so that's 20. There's your delta T1. Similar business for delta T2, all right? You have THO minus TCI, which basically is your TH2 minus TC2. Plug in your values. Here you go. Here's your log mean temperature difference. Because the correction factor is 1, you don't have to do anything to this. Multiplying by 1, you just get the same thing back. If this were not correction factor 1, you would need to multiply the log mean temperature difference by the correction factor to fix the correction factor, so to speak, to fix the log mean temperature difference. That situation happens here in this particular heat exchanger, which is a shell and tube, again, cross-flow heat exchanger. So here, as you can see, all the temperatures are different. There's no phase change happening. So here, you're stuck. You need to use the correction factor. We have to calculate it from the graph. So we need to calculate two parameters first. Number one, we need to calculate R. R tells you which of these blue curves you're going to be looking at. And P tells you the X coordinate. So let's calculate. I have P first. So, by the way, what do these equations mean? Little t corresponds to the tube side temperature. So little t2 corresponds to the outlet of the tube side. Little t1 corresponds to the inlet of the tube side. Capital T's correspond to the inlet and outlet of the shell side. Capital T1 would be inlet. Capital T2 would be outlet of the shell side. So here are the numbers. You can check them yourself. Your outlet tube temperature 65, inlet tube is 90. On the bottom, your inlet shell is 20. Again, inlet tube is 90. And you get your value for P, your X coordinate. Do a similar thing for R to find which curve to look at, and we're seeing that it's the curve labeled 0.8. If we go down here and we look at 0.8, and then we see where 0.357 crosses with it, it looks something like this. Again, this is all estimated. Here's your 0.8. 0.357 is close to 0.36, so it's like something here. Okay. Let me just see something real quick. Okay. So, where does this touch with the 0.8 curve, which is this curve over here? That's going to be just above 0.95, so it's approximately 0.96. So now you would calculate log mean temperature counterflow style. TH1 is THI, TC1 is TCO, right? You would work that out, do the same thing for delta T2. Calculate your log mean temperature as normal for counterflow, but then you have to modify this with your correction factor. And I did that in the final equation, UA times this, right? So F, now the correction factor is going to modify this number. So you get something like this at the end. So it's about 18.22 megawatts. It's not too difficult. Just know that you would need to correct if there is no phase change. Here's another typical question. We have a concentric tube heat exchanger. So we have an inner tube and an outer tube, something like this. And they ask you, how long does the heat exchanger have to be to make the outlet of the hot fluid 70 if your inlet is 400? This is a massive temperature drop. How do we do that, right? So again, you would want to use your three equations. Either you would use the log mean temperature difference or the mass flow rate, or all of them. In this case, you're going to be using pretty much all of them. Now, this is a normal counterflow heat exchanger. By normal, I just mean a simple counterflow heat exchanger. This is a complicated cross-flow or multi-pass heat exchanger. So for the complicated heat exchangers like this one or like this one, you would use correction factor. However, if you just have a basic counterflow or parallel flow, something like this, you don't need to use correction factor. So first of all, let's find log mean temperature difference. It is a counterflow, so we're going to treat it like counterflow. So TH1 is THI, TC1 is TCO. We do a similar thing down here. Okay, we find log mean temperature difference. So now that we have log mean temperature difference, they give us U. Okay, we can kind of find the surface area, right? But we need to find Q, right? So we basically know U and we know this, okay? The length of the heat exchanger is hidden in the area, right? Because the area is the surface area through which convection occurs, which is basically the surface area of this inner tube. But we don't have Q yet. How can we find Q? We use the mass flow rate equations. They give us the cold fluid numbers, so we can just use that. So we find Q from the m dot equations for the cold fluid. Now that we have Q, I have U and I have delta T log mean. Now I can solve for the surface area. But I'm going to actually plug in what the surface area is. It's the soda can area, right? Soda can area of this guy, basically pi dl of this. Okay, in this case is di, pi dil. And then we can basically solve for L. So let's go ahead and do that. So here I plugged in the area, and we solve for L. Plug and chug. We're done. Does the answer make sense? Yes, this is a massive heat exchanger, right? In order to get such a big drop in temperature from 400 to 70, especially with something really simple like this, a simple heat exchanger, it needs to be really, really big. Okay, so the answer makes sense. Next, effectiveness. In order to calculate the effectiveness, you need to find the quote-unquote maximum possible heat transfer. Okay, that's basically what we call Q max. So real Q over the ideal or maximum Q is your epsilon, or effectiveness of the heat exchanger. Okay, so the max Q can be found by taking the minimum capital C times THI minus TCI. Remember, maximum possible heat transfer corresponds to an infinitely long heat exchanger, right? Which doesn't exist, but let's say you have an infinitely long heat exchanger. One of the fluids is going to reach the full temperature drop. In other words, let's say the hot fluid, right? The outlet of the hot fluid, if the heat exchanger is big enough, the outlet temperature of the hot fluid is going to equal exactly the inlet temperature of the cold fluid. We talked about this in lecture. So we need to find the smallest capital C. Capital C is basically m dot times Cp. So we're going to do first for the hot fluid, which is m dot times Cp for hot fluid, and then we do the same thing for, I revealed it here, but if we do the same thing for the cold fluid, you'll see that it's actually bigger. So the minimum one has to be the hot fluid one because it's smaller, right? It's 4197, whereas for the cold it's 6000. So that's how we're going to get Q max. So we can find Q max. Okay. And then we can calculate Q. Now we can calculate Q really from either the hot fluid side or the cold fluid side because we're given all the parameters. So I did it here with the hot fluid side. But if you do it with the cold fluid side, you should get the same answer. Here's Q, here's your effectiveness, and we get our answer, which is 0.22. In this particular case, the effectiveness was not very good. Okay. Let's take a look at the radiation review. So first we talk about a black body because basically a lot of the radiation equations come from the perfect black body equation. So basically, perfect black body is the perfect emitter and perfect absorber, which basically means that the emissivity and the absorptivity of this object, this quote-unquote black body, is just equal to 1. So in other words, it emits everything and absorbs everything. Your textbook shows here an example of a black body, like sort of like a visual example where you have a very large cavity and a very, very small, they call it an aperture, like when you film or when you take a picture, like a camera, right? It has a very small little hole that allows light to come in. In this case, we have a very small aperture for radiation to come in. So basically, the radiation that comes in is going to bounce around in here, as you can see. And because this aperture is so small, it's highly unlikely that the radiation that comes in will come out because it's going to basically bounce around in here. And every time that it bounces and hits the wall, it's going to transfer some of the energy to the wall. And basically, it's going to dissipate and we'll never actually be able to get out. So lo and behold, this has absorbed any radiation that comes in. Now, because this object is, absorbing all this radiation, it's also going to be emitting constantly radiation. So it's also not only is it absorbing everything, but it's emitting everything as well. The reason I use this picture is because we have this concept that if we take an object of interest, so say for example we have here our cat, and we take this cat and we put it in the large cavity, we can basically say that the cavity is a black body. So this is, of course, an abstract example, but let's say this cat is in a large room. If the room is sufficiently large, you can pretend that this is the room, right? You can treat the room as a black body, basically. So that's the whole point of this visual. Okay, so let me just actually, in the classroom, it works better to scroll vertically, but actually like this, I think it works better to scroll horizontally. So placing a small object inside a large cavity is the same as having the object surrounded by a black body. So we have here this classic example. We've done this example in class several times. So the cat sits in a large room. Hint, large room basically means you can treat the large room like a black body. Air temperature in the room is 20 degrees Celsius. The room walls are at 30 degrees Celsius, so the surroundings. Okay. Note also, look, the air is not the same as the surroundings. Sometimes it is, sometimes it isn't. It really depends on the problem. In this particular problem, it's not the same. So just make sure that you take note of that, because T infinity and T surrounding are not the same thing. Okay, the emissivity of the cat's fur is 0.8, the surface temperature of the cat 38.3, heat transfer coefficient is 10 watts per meter squared Celsius. Now I should have said here, I mean it's implied, but I should have maybe to be more specific. And in fact, since I can move things around, I can just edit this now. I should really say the convection heat transfer coefficient. Usually when you say heat transfer coefficient, it's implied that is the convection one, but you could also write radiation heat transfer coefficient. But anyway, just to be absolutely clear, I'll put convection. Okay, so first is calculate heat flux the cat experiences due to convection, then calculate the radiation heat flux the cat experiences. Assume the cat is a gray body, or is a gray body. So gray body just basically means that the emissivity of the cat is equal to the absorptivity of the cat, which is basically not equal to 1. Okay, so gray body has in a way, it's similar to a black body, that epsilon equals alpha, but it's different from a gray body in the sense that it does not equal 1. Okay, I kind of summarize it over here. So I wrote it in two different ways. I said it's because epsilon and alpha cannot be greater than 1, right? Epsilon and alpha are numbers between 0 and 1, where 1 is perfect black body, 0 means that they're emitting or absorbing nothing. So gray body is somewhere in the middle. It cannot be 1, so it's going to be less than 1, but gray body means that epsilon also equals alpha. You could also write it like this, that epsilon equals alpha, but it's not equal to 1, whereas black body, it is equal to 1. Small little thing, it's subtle, but it's important to note. So let's do the first part, which is to calculate the convection. They don't give us the surface area of the cat, so we have to find the flux. And in fact, I think they only, let me just double check, they ask us just to find flux. Yes. So let's do that. So Q convection flux is H Ts minus T infinity. So they give us the H, okay, 10 watts per meter squared degrees Celsius. Ts is the surface temperature of the cat. T infinity is 20. So then we get that the convection, if you calculate the numbers, the flux is 183 watts per meter squared. Okay, and note, by the way, that if you pay attention to the temperatures, which it's important to do, you'll see that who is transferring heat to what, or what is transferring heat to whom, right? In this case, it is the cat that is losing heat to the environment, which makes sense because it's a little bit colder, the cat is warmer, so the cat is giving energy to the room, basically, by convection. So this is only the convection part. Okay, so it would be worth noting, from cat to room. From cat to room. Okay. Radiation. So we have to be a little careful here, because in some questions I ask you, what is the radiation flux the cat emits? what is the radiation flux the cat absorbs, and then I ask what's the net. So those are asking three different things. What the cat emits, that's what we usually call E, the emitted or emissive power, emitted radiation. What the cat absorbs is usually called G, or also known as E radiation. And then the net is the combination of the two. So if we go back, now I'm starting to think maybe the vertical scrolling might be better. Let's see. If we go back, they say calculate the radiation heat flux the cat experiences. So this is basically asking for the net. Okay, it's basically asking for the net radiation heat flux, because it's not saying what is the emitted radiation the cat gives off or whatever. It's saying the radiation heat flux the cat experiences, and the cat is experiencing two forms of radiation. The cat is emitting, but the cat is also absorbing. Okay, so let's write. Basically, the radiation equation is like this, and you have this already in your notes. The flux, right, is epsilon, Stefan Boltzmann constant, temperature of the surface to the fourth power minus temperature of the surrounding to the fourth power. Basically, you just use this formula. But what I want to do is go a little bit deeper and just review where that comes from, because it's important to know. And by the way, this is the net radiation the cat experiences. All right. So basically this comes from Stefan Boltzmann law. So the Stefan Boltzmann law for a perfect black body. So let's actually say here, for a perfect black body, the radiation that is emitted, and actually the way that they write it in your textbook, they use E, is sigma times the temperature of the surface of that object to the fourth power. This is perfect black body. Realistic object. What the realistic object emits, it's the same equation as black body, but now you got to multiply by the emissivity of that object. So a realistic object does not emit all of this energy. It only emits a fraction of that energy as determined by the emissivity of the surface of that object, whatever that is. Okay? So for example, let's say that, in this case, the cat emissivity is 0.8. So basically the cat emits 80% of its radiation. Like if this cat were a perfect black body, this would be 1, so it would be emitting this. But realistically, it's only emitting 0.8, so 0.8 times this. You can do a similar analysis for absorbed radiation, also known as E radiation, right? So because we're treating the surroundings as a black body, right? What this wall, and I usually use the letter G, what this surroundings are sending to the cat is perfect black body radiation, because we're assuming that the room is large enough that we can consider it to be black body. So the incoming radiation is sigma times T surrounding to the fourth power. However, the cat is not going to get all that because the cat has an absorptivity. Now, I gave you a hint. I said the cat is a gray body, so that means that your epsilon equals your alpha. So, in other words, the cat is absorbing 0.8 times this. It's only absorbing 80% of the incoming radiation. So, basically what you have to do is put those two things together. Radiation is a phenomenon, right? The word radiation implies from the object of interest out, like this. That's what radiation implies. You're radiating, right? So absorbed radiation is actually considered to be negative because it's going this way, opposite to the what the word means. So basically the total flux that the cat experiences, and maybe I can write here specifically the radiation flux, is going to be what the cat emits minus what the cat absorbs. And let me just let me do this. Okay, so this one is perfect black body, okay, and this is realistic object. So and just again to be absolutely clear, we'll call this one for perfect black body. What the cat actually absorbs, the realistic one, is going to be just G. All right, so I'm going to write that down here. By the way, I like to usually use green for the emitted radiation and purple for the absorbed radiation. So this is the emitted. Okay, this one is emitted. This one is absorbed. So what is the cat emitting, right? It's epsilon sigma temperature of the cat to the fourth power. What is the cat absorbing? It's what's coming from the surroundings, which is sigma times T surrounding to the fourth power. But then you have to also multiply by the absorptivity of the cat, because the cat is not getting all of that, is only getting a fraction of that. Okay. Let me just, okay. So remember, or recall, gray body, epsilon equals alpha. Like this. So I can replace this alpha with epsilon. So now I'm left with this. I can take out the epsilon sigma as a common factor. And, of course, we're left with our radiation equation that we had before. So that's where it comes from. That equation basically assumes that your object of interest is a gray body. And it turns out it's actually a decent assumption. Most things you can approximate to be gray body. Maybe, do I have gray? Oh, yeah, I could write here in gray body. Okay. Okay. So we basically, the rest is just plug and chug. You plug in, right, your values. Epsilon is 0.8. Stefan Boltzmann constant, sigma is 5.67 times 10 to the minus 8. Okay. Watts per meter squared Kelvin to the fourth power. Don't forget, please don't forget that you must put the temperatures here in Kelvin. If you don't put them in Kelvin, the answer will be wrong, okay? This is not a normal temperature difference because you're taking the temperatures and raising them to the fourth power. So everything gets ruined, right? You can't just interchange Kelvin and Celsius anymore. Now you have to be very careful. So let's actually convert the cat surface temperature. I personally like to use 273.15. Just, I feel like it gives me a little bit more accuracy. I round at the end, of course. Also, T surrounding. The radiation is from the cat to the surroundings, not to the air. The air is only for convection. This is why it's important to note the correct temperature. All right, please be careful of that. Okay, so Q, when you crunch the numbers, becomes 43.71 watts per meter squared. All right. Now, in this case, the number is positive, but what if the number turned out to be negative? If the number turned out to be negative, that means that your incoming radiation is basically dominating. because the number is positive, that means that radiation emitted is dominating. So in other words, the cat overall, the net radiation the cat is experiencing is emitted, not absorbed. Okay? If it were negative, that means that the radiation the cat experiences is absorbed. Okay? So let's just add that here to the notes. So net radiation cat experiences is emitted. Okay. A student asked me in a previous trimester, they asked me, what if instead of the surroundings, what if we had, let's say, between a cat and a dog? And let's say that now I want to know, what does Courage, the dog, the cowardly dog, the famous, of course, what radiation does Courage experience in this case? This is a little bit tricky. It's not difficult, but it's just a little bit tricky because, you see, in general, the cat and Courage are going to have two different emissivities. And if you assume them both to be gray body, right, that makes it a little bit easier, but still these numbers might be different. So I purposefully, intentionally made them different. So how do we do this? So our object of interest, I'd like to, maybe put a red box, is Courage. So what's the net radiation that he experiences? Again, it's going to be the same thing, where basically you're calculating what does Courage emit minus what he absorbs. Okay, so what does Courage emit? And maybe I'll write it with the colors, right? I have my green here. So it's emitted minus absorbed. Okay. So Courage, if he were a perfect black body, would be sigma temperature, SD is the surface temperature of the dog, right, to the fourth power. But he's not perfect, so we have epsilon there. Okay? So that's what Courage is emitting. What is Courage absorbing? First of all, whatever is incoming radiation to Courage is going to be filtered by the absorptivity, right? So he only absorbs whatever fraction is incoming. All right, so now inside these square brackets, I'm going to put in the full incoming radiation. Okay, the full incoming radiation is basically what this cat is putting out. What's it emitting? What is the cat emitting? Well, if the cat were a perfect black body, it would be sigma times temperature of the cat's surface to the fourth power. The cat is not a perfect black body, so we have to consider the emissivity of the cat. Okay, so this is like the total radiation the cat is sending to Courage, but Courage is only absorbing a fraction of that because of this alpha over here. Now, by the way, this is a little lowercase d, so epsilon d, alpha d is referring to the emissivity and the absorptivity of the dog, right? And here for C obviously is cat. So basically the rest is just cleaning this up a little bit. So because we're assuming both of them gray body, I can put epsilon dog, alpha dog. That can just be just make it epsilon dog. It's just a little bit easier that way. Clean this up a little bit. Okay. Couple of common factors. Epsilon dog is common, and also the Stefan Boltzmann constant. So that can all come out like this. So basically now, what do I have left in the parentheses? I have temperature surface dog to the fourth power minus I have epsilon cat temperature surface cat to the fourth power. And that's basically it. Again, you still have to make sure that you put everything in Kelvin, because otherwise it won't work. Okay. So that's basically how you would do this. This would give you the radiation that Courage is getting from the cat. We have to find a name for this cat at some point. Maybe one year we'll name it. Let's do a quick thermal circuit review. So this is chapter 3. Let's take a look at this question. Wind chill, which is experienced on a cold, windy day, is related to increased heat transfer from exposed human skin to the surrounding atmosphere. Consider a layer of fatty tissue 3 millimeters thick and whose interior surface is maintained at a temperature of 36 Celsius. On a calm day, the convection heat transfer coefficient of the outer surface is 25 watts per meter squared Kelvin. But with 30 kilometer per hour winds, it reaches 65 watts per meter squared Kelvin. In both cases, ambient air temperature is negative 15 degrees. So first part is, what is the ratio of heat loss per unit area from the skin for a calm day to that for a windy day? Okay, so let's take this one step at a time. So I already drew the thermal circuit, but let's just go over how I did that. So this is the skin fat layer, right? This is like the internal part, which is staying at a constant 36 degrees Celsius, as you see over here, constant 36 degrees Celsius. And the heat transfer from that part to the surface of the skin will be through solid material, right? The fatty tissue and skin is solid. And that will be by conduction. So we have here thermal resistance due to conduction from this point to this point. Then from the surface area of, from the surface of the skin to the ambient, there will be heat transfer by convection. Okay, now in theory, right, if it were a sunny day, then you would also consider, radiation happening at the same time. But for the sake of keeping the problem simplified, we're just going to consider convection. So it's a cold, windy day, maybe it's really cloudy, it's really dark outside, there's no radiation, only convection. So that's what's going on over here. So heat loss per unit area, that's your flux, that's Q double prime. Let's find it. So let's start, and now I think would be a good idea to switch to vertical scrolling. The flux basically is represented by the current in this circuit. Maybe I'll draw it in red. So the current in this circuit is basically your Q. Now Q I know is not flux. Give me a second. So Q, your current, right, I can write it as a voltage over the resistance. A voltage over the resistance. Now, let's think about it. What voltages do we know? We know the internal body temperature, and we also know the air temperature. Those are basically the analogs of voltage in our thermal circuit. So now I can take the difference of those two, so Ti minus T infinity, write it first algebraically, Ti minus T infinity. And then we divide by the total resistance between the two voltages, which is this plus this resistance, because they're in series, so we just add them together. So that would be what we would call R total. Let's expand a little bit. What is R total? R total is going to be L over Ka plus 1 over HA. And in fact, I didn't need to make this division line too big. All right, now I know we're looking for Q double prime. I didn't forget that. Don't worry. Okay. Don't worry. So watch this. If you take a look down here, surface area is a common factor, right? And it's really 1 over surface area is the common factor. So let's actually take that out as a common factor. So I basically get 1 over area. And here I'm going to get L over K plus 1 over H. All right. Now, you basically have a 1 here, so it's 1 over A. So keep change flip. Basically, 1 over A means that A shows up on top. Okay? In fact, these lines really I should copy, because I know it's supposed to be under this part to get Q, right? So, okay, so that A is going to show up on top like so. And downstairs we have L over K plus 1 over H. Now watch this. If I divide both sides by A, I get exactly on my left-hand side, I get flux. Okay, so it all works out. All right, Q over A basically gets rid of the A. I'm just left with this. I am using copy and paste right now just to save some time, but we end up with this. So basically from here, we end up with Q double prime is equal to this. Okay. The only difference between the calm day and the windy day is the H. Okay, everything else stays the same. So let's do for calm day. For calm day, we get 36 degrees, okay, is the internal body temperature. That hasn't changed. The ambient, T infinity, is negative 15 degrees, okay. L is the thickness of the skin fat layer, which is 3 millimeters. K, the thermal conductivity of the skin, was given to be 0.2 watts per meter Kelvin. And H for the calm day is 25 watts per meter squared Kelvin. Again, in this case, the Kelvin here and the Celsius on top don't really matter, because the Celsius on top is a temperature difference. So even if I had converted these to Kelvin, the temperature difference will still be the same. You're going to get the same answer. Temperature difference in Kelvin is the same as temperature difference in Celsius. Okay, so we crunch the numbers and we end up with flux on a calm day being 9 to 7.3 watts per meter squared. For the windy day, it's going to be the same thing, except we have to change the H. The H now is not going to be 25. Whoops. It's going to be like 65, I think they tell us. So I'll just put a different color so that, you know, you can see the difference visually. Okay, so on a windy day, let's see what happens. You crunch the numbers, and you should get 1678.48 watts per meter squared, which makes sense, right? On a windy day, you feel colder, because of the increased turbulence, right? So it makes sense. Finally, in part A, they just wanted you to take the ratio of the two. So we can just go ahead and do that. So basically, it's Q flux calm over Q flux windy. Right, so basically you get 927.3 watts per meter squared. And then we divide by 1678.48 watts per meter squared, so this becomes 0.552. Okay? Relatively straightforward. Part B, to me, is a little more of an interesting question. They want you to find what is the outer surface temperature on the skin for a calm day and then for a windy day. Find that to be a much more interesting question. So let's do for calm day. So for a calm day, you still have your flux equation. Okay, you still have the flux equation, which looks like, I'm going to write it like this. Let me actually put the algebra first. So your flux equation is actually this guy. I'm abusing copy and paste right now, but it's just to save time. There are a lot of problems to go over. So basically it looks something like this. Okay, this is your Ti minus T infinity divided by the sum of the two resistances. You do your little finesse to get your flux, and then you can plug in your values and we get the flux. So we already actually had this number, but we need this number because now we're going to use the electric circuit to help us find Ts, right? Because now that I have my current here, this is Q, right? Now that I have my current, I know this Ti. In other words, I know this voltage, I know this voltage. Well, I'm sorry. I know this voltage, I know this resistance, I know the current, so now I can find this voltage. Again, we have to do a little bit of finesse because I don't have the picture drawn with flux. I have it drawn with regular current. So let's write it out like this first. So Q, right, is going to be Ti minus Ts over L over Ka. Okay. Now it's actually easier this time because I have the 1 over A, right? It's just easy to take out. So that is going to basically be, it's going to show up on top, so it's going to be A. And now we're going to have Ti minus Ts over L over K. From here, we can basically move the A to the other side, like so, and we get Q flux. And that's going to be your Ti minus Ts over L over K. So now we can find Ts. So Ts is going to be Q double prime times L over K. And see, this moves over here, right? Ts will also move to the other side, but then I got to take the this guy and move it to the right-hand side. So basically I'm going to get actually Ti minus that. Like I mentioned in class, don't do this in one step. I am doing it in one step just because I want to save time. But if I were doing this on an actual, let's say I want to work out the problem off screen, I would do it in several steps just to make sure I don't make a mistake. Okay, here I'm really just saving time. So Ti, I have here 36 Celsius. We have the flux. This is the flux for a calm day. So the calm flux is 927.3. 927.3 watts per meter squared. I have then the length, which is the skin fat layer, which is 3 millimeters. And then K is 0.2 watts per meter Kelvin. You should get that Ts is equal to about 22 degrees, 22.09 degrees Celsius, something like this. Okay. I'm just going to double check with my calculator real quick because you can actually do this another way. I did this another way when I did my notes. And I will show you, I'll explain what the other way is. It's basically still using the thermal circuit. Yeah, we get exactly the same, which has to be the same number, right? So that's actually a good way to check yourself, to perform the same problem in two different ways, and if you get the same answer, you know it's right. So we did it, this voltage divided by this resistance. Because this is a series circuit, this current is the same everywhere. So I could actually have done Ts minus T infinity divided by this, and then solve for Ts. Same business. You get exactly the same answer. If you look at the previous solutions for the final review, you'll see I did it that way. Okay. For the windy day, for the windy day, okay, let's do it over here. So basically, it really doesn't matter which one you do, because Q is going to be different for the windy day, right? For the windy day, Q is this value. So it doesn't matter if you do it like this or like this. I'm going to do it from here to here just for the sake of variety. Okay. So Q, this is for the windy day. For the windy day, Q is equal to, again, we do Ts minus T infinity divided by 1 over HA. Again, the A comes out. Okay. This is not showing up here. It should show up here. My lasso is not working. Okay. So Q over A, which is basically Q double prime, is Ts minus T infinity over 1 over H. So now we can solve for Ts. So now Ts, again, don't do this in one step. I'm only doing it this way, as I said, just to save time. You're going to get here your Q double primed multiplied by 1 over H, so you get this, plus T infinity. So if we plug in our values, the windy T is 1678.48 watts per meter squared. H for windy is 65 watts per meter squared Kelvin. And I can put that in red just like I did before so that you see that this has to change. And T infinity is negative 15 degrees. So then Ts is equal to 10.82 degrees Celsius. Which makes sense, right? If it's more heat transfer, you're going to feel colder, so the temperature will drop. Finally, last part. Last part says, what temperature would the air have to be to get... So what temperature would the air have to be on a calm day to produce the exact same heat loss that occurs with negative 15 degrees on a windy day, right? So on a windy day, I'm losing about 1,000 watts per meter squared. It's more like it's almost 1,700 watts per meter squared, right? Much more than this. So basically the question is, what does the temperature have to be outside such that on a calm day I lose this amount of heat? So clearly outside has to be colder. All right? It would have to be colder, right? So that's the whole idea of like, oh, it feels, it's like such and such degrees outside, but it feels like this. That's basically what we're doing right now is a similar calculation. What does it have to be outside to have the same heat loss, okay, on a calm day? So we're basically now looking for T infinity. However, we're assuming that the heat loss is the same as the windy day. So Q here, double prime, must be the same as that for the windy day. So I need to be losing about almost 1,700 watts per meter squared. Right, so basically here I need Q double prime windy, right? And I'm gonna do this in such a way that I make my life as easy as possible. Okay. So I know this, and I know these guys, okay, the two resistances. So let's write it in that format. Ti minus T infinity and over L. Let me write it first without the double prime, and then I'll put the double prime. right? Because you can take this out, you get Ti minus T infinity. We've done this all, this is now the third time we're doing this, so it should be pretty clear where this is coming from. Something like this, right? So then we can move the Q to the other side, so now we get the Q double prime windy, okay? Like so. You don't want to use this temperature because we actually don't know this temperature. This temperature is going to change now because we have a column H. H is for calm day, and we don't actually know this temperature over here. All we know is the watts. I mean, we can find this temperature, but it's an extra step. We'd have to find this temperature and then set up another equation. It's much easier to just do it in one step, find this temperature, and move on. So in a similar way, I'm just going to solve for T infinity. So T, again, don't do this in one step. T infinity is what? It's going to be Ti minus Q double prime windy times L over K plus 1 over H. Ti is 36 degrees Celsius. Q windy is the 1678.48 watts per meter squared. Okay. And now we're going to have L over K. So that's going to be 3 millimeters divided by K, which is 0.2 watts per meter Kelvin. This is H for a calm day, which should be 25. I'm going to double check that in just a moment. And let me I'll just put the final answer. Let's actually calculate it. So in the parentheses, we have the 3 millimeters divided by 0.2 plus 1 over 25 times 1678.48. I'm going to do 36 minus this answer. And I'm getting about negative 56.3 degrees Celsius. So it has to be really, really cold to get the same heat loss on a calm day. Okay. For completeness, what I'll do, just because it's going to bother me, I will, let me put the arrow. Okay. So from here, we can say, Q double prime windy is basically Q over A, which is this. Hopefully it'll fit. And it just fits. Perfect. So for lumped capacitance method, just make sure you go over the Biot number, know the conservative and customary definitions, know when you can use the lumped capacitance method, right? The Biot number has to be less. So Biot number has to be less than 0.1. Okay. Characteristic length. Characteristic length is basically, it's the length that you would use in your equations, for example, for Reynolds number, Rayleigh number, Nusselt number, that type of thing. In the characteristic length, it corresponds to, in the Biot number, the characteristic length corresponds to this value over here. Now, that value will change depending on whether you're using customary definition or conservative definition. You have the equations in the notes. If you use the conservative definition, your Biot number will be slightly larger than the customary. A good sort of rule of thumb is to do both. And if both of them are less than 0.1, using both definitions, then you're good. You can use lumped capacitance method. That's as far as I want to go into with the transient analysis. I'd want to spend a lot more time with chapter 6, specifically the convection. Okay, so in chapter 6 we talked about convection, velocity boundary layers, thermal boundary layers. Remember that these develop because of the changes in basically in the fluid flow. So maybe I have a picture. So let's actually use this picture over here. Here we have the flat plate, right? So as the air, let's say, is flowing, the air, right when it touches the plate, right at this surface, the air is going to be zero velocity. Now, as you get farther and farther away from the plate, eventually the speed will reach the initial speed, or the ambient speed, or what's called the free stream velocity. Okay, the distance it takes for that to happen is called your boundary layer, or called velocity boundary layer. A similar thing happens with temperature, where the fluid right at the surface is going to match the surface temperature of the plate, but as you get farther away, it'll either cool or heat up depending on the heat transfer. And that distance that it takes to go from the surface temperature all the way back to what the ambient air temperature was, that's called your thermal boundary layer. So these things develop in fluid flow. Now, for a flat plate, the transition between laminar and turbulent is a Reynolds number 5 times 10 to the 5. In short, the Reynolds number tells you whether or not your flow is laminar or turbulent. For a flat plate, and I'm saying that, I'm emphasizing it just because the Reynolds number, or I should say the critical Reynolds number, changes depending on what type of geometry you have. So for a flat plate, the critical Reynolds number, in other words, the Reynolds number where you transition from laminar to turbulent, 5 times 10 to the 5. Here are your Reynolds number equations that you can use. The Reynolds number, as I said, tells you whether we have laminar or turbulent flow. From the Reynolds number, you would go to the Nusselt number to help you find H. Now, Nusselt number, you want to ideally get the average Nusselt number, because average Nusselt number will give you average H. Okay, the difference between average and local is that the average H would be like, as the name suggests, the average of the average transfer coefficient, heat transfer coefficient over the entire plate or up to a certain point, whereas the local H would be at a specific point. Most of the time we want to use the average. I think this is best illustrated by taking a look at a problem. So let's take a look at this one. So air at a pressure of 1 atmosphere, temperature 50 degrees Celsius, is in parallel flow over the top surface of a flat plate that is heated to a uniform temperature of 100 degrees Celsius. So the surface is kept constant 100 degrees Celsius. The plate has a length of 0.2 meters in the flow direction, and the width is 0.10. I drew like sort of a three-dimensional picture here for you. By the way, another good thing, when you have a test and they don't give you a picture, draw a picture. It doesn't have to be perfect, but just draw something because it'll help you visualize the problem. Reynolds number, this is the Reynolds number based on the plate length, is 40,000. So they basically give you the Reynolds number. Great. What is the rate of heat transfer from the plate to the air? We'll deal with this second part that's highlighted in orange in just a moment. So first of all, they say that the entire plate Reynolds number is basically 40,000. Because this is a flat plate, the transition from laminar to turbulence happens at 5 times 10 to the 5. This is not that. This is 4 times 10 to the 1, 2, 3, 4. Right? So it's much less. This is clearly laminar flow. Now, as heat is transferred from the plate to the air, right, the air is going to heat up. So the properties of air are going to change as it heats up along the length of the plate. So the question is, at what temperature should we find the parameters? And the answer is the film temperature. Film temperature is basically the average between the surface and the ambient. In our case, it's the average between 50 and 100. So when you take the average, you should get something like 75 degrees Celsius, which basically corresponds to 348.15 Kelvin. You can look that up in a table, and you get your Prandtl number and K. We're going to need those. All right. It seems that in this particular problem, I rounded it off to, I made it, because it's so close to 350, I just made it 350. That's acceptable. You can do that. If you really want to get it really, really, really close, you can do linear interpolation. So you can go between 300 and 350 and then find whatever the value is at 348. Again, it is still an approximation, but it gets you a little bit slightly closer to the value. Okay. Here are the other properties, specifically nu, the the viscosity, the kinematic viscosity. Okay, so we have the properties here. So from here now, we can start to calculate some stuff. Okay, let's calculate the Reynolds number. Okay. I'm sorry, not the Reynolds number, the velocity of the air. Because typically what's done in these problems is that they give you the velocity of the air and then you have to calculate Reynolds number. But here they did the opposite. They give you Reynolds number and they want you to calculate velocity. So let's find the velocity. We're going to need it later, not for the first part, but we're going to need it later. So let's do that. So your Reynolds number, and this is, they tell you based on the plate length. That's basically telling you that the characteristic length is the actual length of the plate. Looks like this. Okay. And then from here we can solve for the velocity. Like so. And now we can plug in our values and find the velocity. We're going to need it later for the second part, but it's helpful now that we have the properties. Might as well just get it over with. So Reynolds number is 40,000. The kinematic viscosity is 20.73 times 10 to the minus 6. All right. And then of course we divide by the length. The length of the plate is 0.2 meters. And we get our velocity. Let me just shrink this a little bit. That way I can fit the velocity, which is 4.146 meter per second. Okay, now to calculate the heat transfer, you need Newton's law of cooling. So Newton's law of cooling is HATS minus T infinity. That's basically telling you how much heat is transferred due to convection. Now remember that we're doing this for the entire plate, so typically we want the average H. So there's the average H. Now to get the H, which they don't give to us, to get the H, we need to use the Nusselt number, right? So in general, the Nusselt number, average, is basically H times the characteristic length over K. But this is not going to help us, right? Basically, this equation is only useful to get H. What we need is a specific Nusselt number equation for our problem. So in our particular case, it's flat plate, laminar flow. The Nusselt number, average Nusselt number equation for that is here. So we just basically plug our numbers and we get our Nusselt number. Reynolds number was given. Prandtl number is 0.7. And this becomes 117.91. That's your Nusselt number. So from there, we can go back here and we can solve for H bar. So we go ahead and do that. So let's see what we get. K was 0.0299. The length of the plate was 0.2. So H bar turns out to be 17.63 watts per meter squared Kelvin. We can now calculate Q. It's just, at this point, it's just plug and chug. You can see above the Q equation. There's Q. The A is the surface area of the plate, specifically the surface area where there's convection happening, which is the very top. So it's going to be the length, 0.2 meters, times the width, which was 0.1 meters. Just make sure I have the right dimension. Yep. Okay, and then the difference in temperature, Ts, is 100 Celsius, and T infinity, the free stream temperature, was 50. So we get here 17.63 watts, which is kind of funny. Because when you do this, it's going to be 1 over 50. This becomes 50, so they cancel and you just get the same number as this. It just happened that way. The numbers turned out that way, but don't make it a rule. It's just, as I said, it just happened that way. Now, before we go on to the second part, let's actually let's see what it asks us. Second part says, if the free stream velocity of the air is doubled, so double the velocity, and the pressure is increased to 10 atmospheres. So initially we start off at 1 atmosphere. Now they want to increase it. What is the rate of heat transfer? So let's see what happens. Basically what we're doing is we're taking the pressure, which is 1 atmosphere, and multiplying it by a factor of 10. So basically what I wrote over here is that your new pressure, P2, let me change the color like this. P2 is 10 times P1, okay? Now, that is going to affect the viscosity. The pressure has a big effect on the viscosity, so we have to see what's going to happen. So, remember that nu is mu over rho. So nu is basically called kinematic viscosity. Mu is dynamic viscosity. Now remember that as pressure goes up, the density goes up. So if my pressure increases, this guy goes up, which consequently means that kinematic viscosity nu goes down. So it's inversely proportional to the temperature change. So we can set up a proportionality like this. We can write pressure 1 over pressure 2 is kinematic viscosity kinematic viscosity 2 over kinematic viscosity 1, because they're inversely proportional. And basically what we want to do now is solve for kinematic viscosity 2. So the 2 corresponds to the new condition and 1 corresponds to the old condition. So let's plug in for P2, right? P2 is 10 times P1. That's going to help us out a little bit. Like this. The P1s cancel. And here you can clearly see, if you solve for nu 2 is basically nu 1 over 10. All right. So now we have to adjust the Reynolds number and see, maybe this changed it, right? Are we going to get turbulent, or we still have laminar? So your previous Reynolds number was basically the speed, the U infinity 1 times L over nu 1. This is like the Reynolds number in condition 1. Reynolds number in condition 2, you have a different speed, the length of the plate is the same, and your kinematic viscosity is changed. The new speed is twice the old speed, like this. So I'm just plugging in. Okay, the new speed is twice the old speed, and your new kinematic viscosity is the original kinematic viscosity divided by 10. So if I just shift some of this algebraically, basically you're going to get 20 times U infinity 1 times L over nu 1. Well, if you notice, this is basically your previous Reynolds number. So basically the new Reynolds number is 20 times the old one. That just simplifies your life a little bit. So Reynolds number 2 is basically 20 times 40,000, and this becomes 8 times 10 to the 5. Now, because this is a flat plate, this is now greater than 5 times 10 to the 5. So now we have turbulence. Okay, now we have turbulence. So we have to see several things. First of all, let's find the new speed. It's pretty easy, the new speed. The new speed is basically twice the old speed. That's why we calculated the speed previously. So it's 4.146 meter per second. Let me just double check. Yes. So the new speed is 8.292 meter per second. That's your new speed. But now we have to find out where is the turbulence happening, because that's also going to affect our equation. I have a picture here. Is the turbulence happening here? Is it happening right at the very end? Is it happening right at the very beginning? All these things make a big difference. So let's see where it happens. The way you do that is by calculating, you can basically calculate the critical Reynolds number. Okay, so how do you calculate critical Reynolds number? Critical Reynolds number happens at the critical distance. In other words, where the transition to turbulence occurs. So it looks something like this. Okay, the U infinity is for the new condition, so in other words, U infinity 2, and nu is also for that condition. So basically, all we got to do is solve for x critical when our Reynolds number critical is 5 times 10 to the 5. So basically, let's solve for it. So we get here Reynolds number times nu over U infinity. Like so. Okay, so if I plug in Reynolds number 5 times 10 to the 5, I'm basically calculating at what distance is the Reynolds number becoming 5 times 10 to the 5. Is it happening right at the beginning? Is it happening somewhere in the middle? Over here at the very end? Right? That's basically what we're trying to find out. At what distance is the flow going from laminar to turbulence? That happens at Reynolds number 5 times 10 to the 5. We know that for the whole plate, at some point it's going to be turbulent. We just don't know where. Okay, so that's what we're looking for right now. So let's plug and chug. Here is the new, this is the old nu. And to get the new one, I just need to divide it by 10 like this. The new speed was down here, 8.292 meter per second. And this will turn out to be 0.125 meters. Okay, I already had the drawing. I wrote it here from doing the problem previously, but this is how I got that number. So basically, the critical Reynolds number, the critical distance is at x equal to 0.125 meters, so right over here, somewhere in the middle of the plate. Okay, so that is actually very helpful because that will tell us what equation to use. So because the turbulence is happening somewhere in the middle of the plate, we need to use what's called the mixed condition equation. Okay, the mixed condition equation, we derived it. There was basically involved having to do an integral from 0 to the critical distance and then from critical distance to the end of the plate. But because we derived the equation, we don't have to do that integral every single time. It's the same integral every single time, so we don't need to do it all the time. We did it once, we have the equation, we can just apply it and move on. So the only thing to remember is that for the flat plate, this constant A is just 871. Okay? So let's calculate. So it's going to be 0.037. Your Reynolds number is 8 times 10 to the 5. Raise it to the 4/5 power minus 871. And then your Prandtl number was 0.7. Okay, we'll raise that to the 1/3. And we should get an average Nusselt number of 960.6. So now that we have that, we can go to the general Nusselt number and solve for H. So let's plug in the numbers. So H bar becomes 143.61 watts per meter squared Kelvin. finally, we can just calculate Q. And you can, at home, you can make a prediction if it'll be larger or smaller, just for fun, just to see. So H bar, we put into H. The area is just the length times the width. And here we have the Ts minus T infinity. So this is going to be 143.61 watts. Okay. If you guessed that it would go up, it did. Okay, it went up by quite a lot, almost by a factor of 10, slightly less than a factor of 10, which is significant, which makes sense, right? If you increase the pressure, increase the speed, you're going to get more turbulence, you're going to have more heat transfer. It makes sense. Okay. So the next question was basically a homework question. So let's take a look. Exhaust gases from the manufacturing plant are being discharged through a 10-meter tall exhaust stack with outer diameter 1 meter. On a particular day, wind at 27 Celsius blowing across the exhaust stack with a velocity of 10 meters per second, while the outer surface of the exhaust stack experiences radiation with the surrounding at 27 Celsius. Solar radiation is incident on the exhaust stack outer surface, and both emissivity and solar absorptivity of the outer surface are 0.9. The exhaust stack outer surface temperature is 126.7 Celsius. Estimate the heat loss. So this is basically going to be a cylinder in cross-flow, essentially. Okay, cylinder in cross-flow. As you can see, we have wind blowing, so it's cylinder in cross-flow. Still, we need to find a couple things. So let's make some notes. First of all, Ts is the surface temperature of the exhaust stack, which is 126.7 Celsius. We can convert that into Kelvin, so I get here in Kelvin is 399.85 Kelvin. And you know what? Let me switch this to horizontal. And maybe let's shrink this a little bit. Too much, like this is good. So this is going to be 399.85 Kelvin. Then we have the surroundings. They mentioned that T surroundings is 27 Celsius. Okay. Basically, you're going to treat the surroundings kind of like the exhaust stack is surrounded by a black body. You can sort of think of it like that. Surroundings being like the atmosphere, other things around it. Overall, it's 27 degrees Celsius, and you can approximate that essentially as your surroundings. In other words, you can draw this sort of situation like this, right? I meant to make it like this, right? Like this, and your surroundings are whatever, 27 Celsius. You could think of it that way. Okay, that there'll be radiation exchange with the surroundings. So let's write that down. So SUR is basically having to do with radiation. Surroundings. That's this. Okay. Then you have T infinity, which is the ambient air temperature, which they also say is 27 Celsius. That's great. Okay. You are going to need a film temperature so that you can find the properties of the air for the different, convection stuff. So here comes the film temperature, which is the average of the surface and the ambient. I'll do it here in Celsius. So in Celsius, it becomes 76.85, but when you convert it to Kelvin, it's 350. I actually, you'll notice I modified the problem such that you get a number that's going to be on your chart. Okay, so we're going to write down some values that are meaningful. We want thermal conductivity. We're going to need that. We're going to need mu here. Prandtl number we will need also. And of course also we will need new kinematic viscosity. All right, so we have all that, just gathering all the information that we need. So the next thing, this is again cylinder and cross flow. So this is falling under the category of forced convection. So there we're going to need Reynolds number. So we'll need to find Reynolds number. Now remember, for cylinder and cross flow, Reynolds number we evaluated a little differently. We do not use U infinity. Instead, we have to use something called the upstream velocity, which they call V, times the diameter, and we divide by nu. That part is the same. So the upstream velocity, let's see what it is. Basically, it's the velocity that's unobstructed by the cylinder. So in this case, the wind is blowing at 10 meters per second, and that's far away from the stack, so it's unobstructed by the stack. So that would be the velocity that we would need. All right, your diameter is 1 meter, and then nu we just had it from the table. So your Reynolds number becomes 478011.4223. So for cylinder and cross flow, the equation that you need for Nusselt number, or average Nusselt number, I really should put like this, will be the Churchill-Bernstein. Okay, so basically you have to end up plugging into this equation. I plugged it in already for you just to save some time, the values that you need. So the Nusselt number will end up being 670.831. Okay. Now I already wrote it here, but I'll sort of do it here in my laser pointer. Your Nusselt number, right? When you're talking about a cylinder, right? Normally it's H, L over K or something, right? Or HX over K. But for a cylinder, this L becomes diameter. Okay, so that's where this comes from. So just plug in our values. It's pretty straightforward at this point. I wrote it twice. Sorry about that. K, we had it from our material properties. Diameter, 1 meter. Heat loss due to convection. Now we just use Newton's law of cooling. Pretty straightforward. So H, we just calculated it. Your area would be the surface area of the cylinder. That's your pi dl. So pi, diameter is 1 meter. Length is 10 meters. And then we have the difference in temperature. So here comes Q convection. So Q convection will end up being 63034.7 watts. We're not done. We still need to do the radiation part. Now the radiation part in this particular question is a little bit more involved than usual. So first of all, you will have the radiation exchange with the surroundings like we normally do for Stefan Boltzmann. Okay, but in addition to that, we also have the radiation they call the solar radiation. That's in addition to the radiation from the surroundings. So let's just read a little bit about that. They say here solar radiation is incident on the exhaust stack outer surface at a rate of. So they basically give you the solar radiation Q, the flux basically. Okay, so you have that already. I even wrote it down for you over here. They give you that, the solar radiation. Okay, they give it to you in the form of flux, but you can still work with it. It's usable. Okay, the radiation, so what we have to consider is not only the radiation from the sun, but the radiation that the stack, exhaust stack, experiences with the surroundings, right? That's the normal Stefan Boltzmann. So let's just write some notes. Because the object of interest is the exhaust stack and the solar radiation is incoming or incident, right? That's considered what's called irradiation, which uses the letter G. So basically, when we write our equation, you're going to have to subtract the solar radiation. Okay, we subtract it because it's irradiation. Remember that Q due to radiation is going to be whatever is emitted minus whatever is incident or attacking the object of interest. Okay, so our total radiation is basically the radiation that the stack experiences with the surroundings. Just maybe it's better to put, surroundings, perhaps. I have it at, maybe, I don't want to confuse you. So let's just say the stack without, just the stack itself. And then we have Q radiation solar. Now the solar, we have to subtract it again because it's E radiation. In other words, it's incident or incoming. So the Q rad stack is something that we already know. We were familiar. It's the Stefan Boltzmann equation. It's basically, and they even tell us, you might be asking, oh, can we treat exhaust stack as a gray body? The answer is yes, because they say in the problem that emissivity and absorptivity are 0.9. So that basically is implying it's a gray body. So we can use this equation with no problem. Now, we have to be a little bit careful here, right? Because this is what's incoming, but remember the stack has an absorptivity. Okay, so the stack is not going to, this is not all of this is going to be absorbed by the stack, a fraction of it will. So basically we have to multiply by alpha, which at the end of the day, alpha is the same thing as epsilon. So we'll be able to take it out as a common factor, but let's just do one step at a time. So we basically have to write it like this. This is the more correct way of writing it. Now keep in mind that all this is a flux. So if you want to get just Q by itself, right? Just this is important. This is a flux. So if you want to combine it with convection, right, you have to convert the flux into just regular Q. In other words, just convert it into watts. So we got to multiply the whole radiation by surface area. So to get rid of the double prime, we multiply by surface area, okay, and we end up with the following. And here I'm going to note that basically for this guy, epsilon equals alpha because it's, we're told in the problem we can assume gray body. So that's going to come out as a common factor, which is nice. Okay. We also have the surface area is pi dl. I'm going to take out that epsilon as a common factor. So basically I'm left with sigma ts to the 4 minus t surrounding to the 4. Minus G solar, or G solar. Yes. Okay, here's your area, and there's the sigma. So now it's just smooth sailing. Diameter is 1 meter, length is 10 meters, epsilon is 0.9. Stefan Boltzmann constant. Okay, and now we have the temperatures. That's why I wrote them in Kelvin earlier so that we can plug in a lot easier. So TS in Kelvin was 399.85. Then T surrounding was 300.15 Kelvin. And G solar, we need to squeeze it in here a little bit. I will use my resizing trick. So this should be 1400 watts per meter squared. Okay, notice that this term is still a flux, this term is still a flux. It will cease to be a flux when it is attacked by this surface area, which will turn it back into regular Q. So you're going to find that you're going to end up with a negative number. It's going to be negative 11616.4 watts. So what does this mean? The negative basically means that the net radiation is actually, it's absorbing. The exhaust stack is basically, the net radiation is absorbed. It's absorbing stuff. Okay, so that's important to note. So I'll add that here. Net radiation, the minus sign means the net radiation is absorbed. Okay. So finally, you just put the two together, and that's it. So this is Q loss. Total is Q convection plus Q radiation total. Q convection is 63034.7 watts, and then we have here 11616.4 watts. So this becomes 51418.3 watts. Okay, and that's basically it for this problem. We have a couple more left in the final review. Okay. Basically, what do we have left? We have the internal flow question, which should be relatively straightforward, but we'll go through it. And then we have the natural convection problem, if I'm not mistaken. Yes, natural convection. That's basically it. Okay. So this is the internal flow question. It says here, consider pressurized water, engine oil, and it seems like sodium potasside, I guess you would call that, flowing in a 20 millimeter diameter tube. Okay. So they want you to find mean velocity, hydrodynamic entry length, and thermal entry length for each fluid when the fluid temperature is 366 Kelvin and flow rate is 0.01 kilogram per second. So the first part for the mean velocity is pretty straightforward. You guys already seem to know this equation, which is good. You were taught well in fluids. M dot is basically rho VA, right? Now the V, or velocity, actually refers to the mean velocity. So you basically have your equation right there. So now you can solve for the mean velocity, UM. That's going to be M dot over rho times A. Now, I should note that the A that we're referring to here is the cross-sectional area through which the fluid is flowing. So cross-sectional area of flow, like so. Okay? So let's write that down. So we have here M dot, we have rho. The cross-sectional area is pi r squared. We have the diameter, though, so I'm going to write it as pi d squared over 4. Okay, but that's your cross-sectional area. You can plug in your numbers, and it's quite straightforward at this point. Probably for this part, the most difficult part is looking up rho, because you'll go to your table. First of all, you have to do linear interpolation, which is not great for this problem. But the second thing that may confuse you is you may not, looking at the first time, you may not see rho. You're like, oh my God, where's rho? But then you take a look here, specific volume. If you look at the units, you'll see it's literally the reciprocal of rho. So basically, you can just take the reciprocal of the specific volume, and that gets you rho. And that's basically how I got rho down here. Okay? So never panic. There is always a solution. I shouldn't say always, but most of the time there is a solution. Okay, so diameter is I apologize. It was just it seemed like my AirPods randomly connected, and I know when that happens, it's gonna mess up the whole audio. So I just wanted to avoid that. Hopefully, it doesn't do it again. All right, so mean velocity will end up being 0.033 meter per second. Boom. So now they want us to find the hydrodynamic entry length and the thermal entry length. Before we can do that, we have to establish whether or not the flow is turbulent. Okay, so let's take a look. So this is a good review. Find Reynolds number to see if laminar or turbulent. Okay, your Reynolds number is quite similar to what we had before for external flow, except for free stream velocity, we use the mean velocity, and instead of x, we use diameter. So it looks something like this. You could also, of course, replace these guys with nu, if you so desire. It's the same thing. Okay. Let's plug the numbers in and see. Mean velocity is 0.033 meter per second. We just did it. The diameter was 20 millimeters. And the viscosity, the dynamic viscosity, 306 times 10 to the minus 6 Newton second per meter squared. So you're going to get that your Reynolds number is 2080.46. So if we were in class, my question would be like, is it laminar or turbulent? And I would wait for you to answer. So I'll give you a moment. If you said that it is laminar, you are correct. Okay. For turbulent flow, it has to be 2300 or greater. So this is in fact laminar flow, which is going to be useful because it's going to tell us which equation we need to use to find the boundary layer. The hydrodynamic and the thermal entrance length. Okay. By the way, this is an image to show you what's going on. So basically, what is the entrance length? It's how long it takes for all these boundary layers to just collide with each other. So the hydrodynamic entrance length has to do with when the velocity boundary layers collide. The thermal boundary length has to do with when the thermal boundary layers collide. More often than not, these do not coincide. One will happen before the other. It doesn't mean it'll never coincide. Sometimes they may happen at the same time, but it's quite rare. So here is just a quick review of hydrodynamic entry length. I defined it as I just said it. For laminar flow, this is your equation. For turbulent flow, the equation is not exact, but basically it's something, it has to be greater than 10 diameters. Okay, for turbulent flow, for the hydrodynamic entry length. For the turbulent flow for thermal entry length, you'll see that the thermal entry length is roughly the same. It's about 10 diameters as the hydrodynamic entry length. The laminar thermal entry length is slightly different, but it's a big difference. You see here we got Prandtl number, here we don't. So for the thermal entry length, it depends on the Prandtl number. For the hydrodynamic, it does not. So at this point, it's a plug and chug game. Okay, so to find the hydrodynamic entry length, we just literally plug in the numbers. It's quite easy. So this becomes 2.08 meters. Okay. If you're wondering what the subscript means, it means fully developed. H is hydrodynamics. So it's the distance it takes for the flow to become hydrodynamically fully developed. We do a similar thing down here, except now we're going to do the thermal entry length, and the equation for thermal entry length also involves the Prandtl number. In fact, the way they like to put it is like this, although it really doesn't matter. Your Prandtl number is 1.91. Here's your diameter. That should be a multiplication sign. I'm not sure why it came out looking kind of evil. Okay. So here is your fully developed thermal entry length. It's slightly larger, right? So basically the fluid will become hydrodynamically fully developed before it becomes thermally fully developed in this particular case. And I believe that's it for this problem. We'll now look at the last one, which is the natural convection. So this is really important because a couple people, more than a couple people, a lot of people made this mistake. Rayleigh number is for natural convection. Okay, Reynolds number is for forced convection. So please make note of that. If you're doing a natural convection problem, it is the Rayleigh number. Rayleigh, like this, RA. Okay. Natural convection is also known as free convection. Some key words to look out for: quiescent air. That usually means natural or free convection. Quiescent basically means like undisturbed, kind of like quiet, sort of. It has the same root. So whenever you see that, that's basically my cue to you, like, hey, this is natural convection. Okay. Rayleigh number, this is your equation. Okay, if you have a cylinder, the L here, it's sort of like a characteristic length. This L becomes diameter if you have a cylinder. Know which equations to use. For the cylinder for natural convection, you're going to use Churchill and Chu. Okay, Churchill and Chu for cylinder. If that helps you, think of it, Churchill and Chu, right? They both start with a C for the cylinder. For natural convection, it's Churchill and Chu. For the cylinder and cross flow, it's Churchill and Bernstein. Okay, so however way it helps you remember it, find a way to remember it so that you don't confuse the two. Okay, let's take a look at this question. So some of the sections we did do this question, and some of them we did not do this question. So that's why I'm just going to do it now. In pretty much all the sections, I added a little bit of artistic expression here, right? So we have here the Mona Lisa, which is kind of cool, but I also wanted to add in the little cat guy here for fun. Put him over here on the little ledge. Okay. So during a winter day, the window of a patio door with a height 1.8 and a width 1 meter shows a frost line near its base, like this. This is pretty common. Okay, the room wall and air temperatures are 15 degrees. Pretty cold. Usually room temperature is around 20, but it's okay. Some people like it colder in their house. Fine. 15 degrees is okay. Part A says, explain why the window would show a frost layer at the base rather than the top. And some of you may have wondered this. So part A, I'm not going to give you like a question like that where you have to like write an essay. Although it's not really an essay at this point, but let's talk about it. So basically what's happening is it's very similar to the flat plate. The only difference is that we have natural convection. So you can think of this not as a flat plate that's horizontal, but perhaps maybe a plate that's vertical. And what's happening is because of, the hot air is rising and the cold air is sinking, it's as if you have a boundary layer that's forming like this. And that's basically what's happening. Your boundary layer is going to get thicker here near the bottom because the colder air is basically more dense, and it's going to collect near the bottom. And because your boundary layer is thicker there, the heat transfer in that region will be worse, basically. It's going to be more difficult for heat to transfer there. And because of that, you're more likely to have the formation of frost on the lower side. Okay, that's essentially what is talked about here. I wrote it already for you. That's basically what's happening. Okay, the boundary layer here near the end is going to be thicker, and it's going to be more difficult for heat to flow. Okay. Again, the cold air is more dense and accumulates at the bottom of the window. So both these ideas are related. Okay, the formation of the boundary layer has to do with the fact that the hot air is rising and the cold air is tending to sink to the bottom. Okay, that's part A in a nutshell. Part B is interesting. They say estimate the heat loss through the window due to convection and radiation. And they also ask us to find out how much money we're going to lose, right? Because if we lose heat and we're trying to heat the house and heat is escaping, we're basically throwing money out the window, pun intended. Okay? So we need to find out how much money we're losing. It's kind of an interesting question. So let's see. First of all, we need the correct properties, so we're going to need to find the film temperature. That's very important. Okay. Film temperature, again, is the average of the surface and the ambient. So it looks like this. The surface temperature of the window, they say, is 0 degrees. That's also probably another reason why stuff is freezing. 0 degrees is the freezing temperature of water. Now, why is it happening at the bottom? Again, we explained it already. So this is going to be 7.5 Celsius, which in Kelvin is 280.65 Kelvin. This textbook really likes making you do linear interpolation. I don't think there was one question where the temperature actually was on the chart. Anyway, fine. We do linear interpolation. We get our properties. Now, we do need this variable beta. Beta is actually the reciprocal of the film temperature. The only thing to remember is that you have to put the film temperature in Kelvin. Please put it in Kelvin. If you forget to put it in Kelvin, it will be wrong. So it has to be like this in Kelvin. I will put a note here. Must be in Kelvin. Okay. So finding the Rayleigh number is just a plug and chug deal at this point. G is your gravitational constant. There was 1 year where people were misunderstanding G. I don't know. Somehow they thought that this G looked like a rho. So let me draw it again. It is not a rho. It is the gravitational constant G. Okay, it is G. Okay, here comes beta. And now we have the temperatures, right? So we have T infinity is the ambient temperature. Then we have here, of course, the surface temperature, which is 0. The length of the window, which is 1.8 meters. Prandtl number is 0.701. And then we have the kinematic viscosity. Again, I carried many decimals after my interpolation just so that we avoid rounding error and we only round at the end. Don't forget to square this guy on the bottom. That's another common mistake. People miss that. Okay, so we plug the numbers in. Rayleigh number is 1.06788 times 10 to the 10. Okay. So now you would basically need to go back in your notes and find out which Nusselt number equation you need. Remember, it is natural convection. So you would have to go back in your notes. Okay. So we have to go back to the natural convection chapter here. Okay. And you have your table here, right? So we don't have any cylinders. We don't have any angled plates. We just have a straight vertical plate. Here is your equation. Boom. That's what you use. Okay. And there it is. Okay, you plug in your values, and your Nusselt number should be 257.1. Then you use the general equation of Nusselt number. You invert it, nuke over L. Okay. And you find H. Smooth sailing so far. And H becomes 3.535 watts per meter squared Kelvin. There's a little dot here. I'm going to erase that. Okay, there's your H. And finally, you just have to plug into the convection equation. Your convection equation is your normal, H, A, Ts plus T infinity. Now, they also ask about radiation. Radiation equation is your Stefan-Boltzmann equation. Epsilon sigma A Ts to the 4 minus T surrounding to the 4. They don't say anything about gray body, but most of the time you can approximate everything as a gray body, so we'll assume gray body so we can use the Stefan-Boltzmann equation. There's a slight mistake here. This should not be Ts plus T infinity. It should be Ts minus T infinity. You're going to notice when you do this that your overall Q will be negative. And that's okay. Why is it okay? It's much colder outside than it is in the room, and heat is escaping the room. So because heat is escaping the room, it basically ends up being a minus. It's going from the room, basically from here to here, right? So it's going to be minus. Minus sign just indicates the direction, so it's no big deal. All right, so now we just plug in our values, and we're basically, this problem is basically done. At least this part. We have one last part when we talk about the money. So the area is 1.8 meters is the length. The width is 1 meter. Ts is 0. T infinity is 15. Epsilon, they gave it to us. I think it was 0.94. You know what? I'm going to put it on 2 lines because I know it's not going to fit. Sigma 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the 4. Again, area is the same, 1.8 times 1 meter. Here you must put in Kelvin. Don't forget. In this case, the surrounding was also 15. All right. So this will actually turn out to be a negative number. I have it written in my notes. I wrote both of them. So basically your convection becomes negative 95.457 watts. And then your radiation is negative 127.333 watts. And this overall will be negative 222.79 watts. again, as a reminder, minus means heat goes from room to window. Okay, maybe I can make that a little bit better. Maybe like that. Okay. Now we talk about the money. Okay. They tell us that the utility rate is about 8 cents per kilowatt hour. 8 cents per kilowatt hour. So basically we want to calculate how many dollars a day we're throwing out the window, right? So basically this is the Q that we're throwing out the window. We're throwing it out the window, literally throwing it out the window. So we're going to calculate how much, because we have to pay for that, right? We have to calculate how much money that's equivalent to. So I want to know dollars per day. I want my final units to be in dollars per day. Okay, let's just start out with the 8 cents per kilowatt hour. This part's easy. You know, 1 kilowatt is 1,000 watts. This kilowatt hour, I drew it kind of funny. Let's make it a little, give it some space. Okay, so that will get rid of the kilowatts here. We still got watts on the bottom, but we can get rid of the watts because we have to multiply by the number of watts that we're throwing out the window. You'll notice here I'm not putting a minus sign just because the minus sign is indicating direction, which I don't care about at this point. I just care about money. I already know that the direction of the money is out the window. Okay, so I don't really need to put that in my calculation. So this watts will cancel this watts. So now basically I need to convert from hours to days. This should be pretty easy. It's just 24 hours in 1 day. Okay. And basically we're going to get the dollars per day that are going out the window are $0.428, which is approximately 43 cents a day. Okay, 43 cents a day. Doesn't seem like a lot, but it over time will start to add up. And this is why people upgrade their windows, or they put curtains, or maybe they upgrade their windows and put curtains to reduce this this heat loss. And that's basically it for the final review. Okay, if you have any further questions, feel free to email me, both at the Academy email, but if it's something, let's say I'm not on campus, use my Gmail, John. It doesn't fit there. Let's do it here. It's no capitals. It's like just john.kolef@gmail.com. Okay, you already have this email. I told you to write it down on your syllabus, but in case you didn't write it down, you have it right now. It's been a pleasure, everyone, and good luck with everything, and hope to see you again in the future, in future classes.